STAT340 week 11. So the contents of this week. First of all, we are still talking about classification that we started on last week. So we will revisit this, and I will just briefly also mention this possibility of dummy coding using regression, ordinary regression, because this is sort of an introduction to today's topic. We will extend the regression idea that we have seen before to also cope with classification in a good way. This is a way of doing it, but it's not the best, but it works sometimes. The logistic regression, that's the one we are going to focus on this week. So that's sort of a regression technique that works for cases where we have categorical responses. And this introduces the concept of generalized linear models. So we will have to say a few words about that in general. And also next week, we will you will see some continuation, you could say, of this topic, but not for classification purposes, but for count data. Yeah, generalized linear models is sort of a generalization of the regression setting, you could say. Yeah, we have to say a few words about the concept of odds ratio, because this has to do with the interpretation of the output we get from the logistic regression to help us understand the output. And we can test for significant effects and so on, as we have done before. We also can do variable selection here now in a way much similar to what we have done for regression models. If you go back to week 6 and 7, we talked quite a lot about that. So we will see some of the concept we saw then, the Akaike's information criterion, and also the lasso method implemented for logistic regression. So we can actually do variable selection in exactly the same ways as before, and that's nice. Okay, logistic regression. If you want to read about this in our book, you find it several places actually. First, in chapter 13, there's some more sort of general about generalized linear models. It's not so much on logistic regression, because there are several ways of making generalized linear models, right? This is only one of them. But you can start looking there, and then in chapters 16 and 17, it's more about this concept here, and especially 16, I would say, because 17 is also the same topic actually, but I don't know. The author of this book has decided to make this into 2 different chapters. I would perhaps not have done that, but okay. So let's go back to last week where we start talking about classification problems. So the response is now categorical with C classes, right? Capital C classes. So it's actually a factor with this number of levels. And that's different from what we have done prior to last week. The predictors are, as we have seen before, they can be quantitative or categorical. And in most cases they are quantitative, right? So it sort of generalizes, or it's a variant of the regression. The only difference is the response. We also saw then last week that if you, for each of these classes or factor levels, right, can compute this here, the probability of the factor level or class condition upon the predictors. So the probability of class C given the data in xi, right? This is a row in the data table, right? xi. If you can compute this, where this is then, yeah, that's the data case, a row in x, yeah. Then for this given xi, we have one probability for each class, because you can do this for class 1, class 2, class 3, and so on, right? And then the base rule says assigned to the class with the largest probability. So these posterior probabilities, that we call them, are the key, right? If we have these, we have solved sort of the classification problem. And not only that, we also have a good measure of how sort of certain we are, right? Because we saw that last week. If you have a posterior probability which is almost the same for two classes, then you are on the border between these two classes, and you are really uncertain. You assign to the one with the largest probability, but if this is only tiny much larger than the other one, you're pretty uncertain. But if on the other hand, if the posterior probability is very high for the winning class, you are pretty certain, right? So having these posterior probabilities is very, very informative. The problem is, how do we compute them, right? And we saw last week how we can use LDA or QDA to compute this. We will now see a different way of doing this. That is more similar to the methods we have seen before in this course. So we now devote special attention to the two-class case, where there are exactly two classes. So capital C is 2. We have two classes, right? But we will see later today that we can extend this to multi-class problems. But we start out with a two-class problem. It's always simpler, and the logistic regression actually only works originally for two classes. And this is the chapter 17 in the R book where they focus a lot on this. So let's go back to regression, actually. Dummy coding and regression. I think we actually did this in an exercise in either week 6 or 7, I don't remember, where we tried to use PLS as an explorative tool. If you go back to the exercises, I think it was week 6, using PLS as an explorative tool, then we did actually this. What am I talking about? Okay, let's say we now have the response with two classes. Then make a new response variable, which is no longer categorical. We call it y dummy because this is now numerical, but it only has the value 0 or 1. So you can see that it's sort of categorical, but it's not. These are not categories. I mean, 1 is bigger than 0. Right? This is numerical. But you only pick two numerical values, and it doesn't really have to be 0 and 1 either. Sometimes we use -1 and 1. The point is that you sort of replace the categorical original y variable, or you don't replace it, but you add another variable which is similar to it, but it is numerical instead. And then you fit the regression model using this one as the response instead of the original one. And then you are back to a straightforward regression situation, right? Where you use this and all the x's as predicted as before and so on. And then you can sort of predict if this predicted y dummy value is now larger than 1/2, you are closer to 1 than to 0, right? Then you have class 1. And if you predict it to be less than 1/2, you are in class 0. So this is sort of, and this is exactly what we did with the PLS explorative, but we didn't actually do the prediction. We used it only to compute some scores and so on, to explore the data. But this is also sort of legal, right? So let's look at an example here that we will see more of shortly. It's the lizard dataset in our R package, where we want to classify. We have data for some lizards, and for each lizard we have the sex, female or male, right? So these are our two classes now, and we want to see if we can sort of classify a lizard based on some measurements of its body, because it may not be so easy to to see what is a female and a male lizard, can we make some simple measurements on the lizard's body, and from that infer what sex it is, right? So let's only look at one of these x variables, mass, which is actually the weight. You simply weigh the lizard, right? There are more. We will see more of this data set shortly. But let's consider only this one single predictor x and one response y here. And here is how the data look like now if we do this dummy coding. And here I have now decided that female is 1 and male is 0. Right? Can you see that? So I say that, okay, we replace all incidences of female with a 1, and we replace all the incidences of male with a 0. So that means the y, this is now the y dummy sort of axis, right? It's either 1 or 0, nothing in between, of course. And here is the x-axis, the mass, right? So now we can see that, okay, the females tends to be smaller than the males, right? We can see that tendency. Males tend to be heavier, bigger mass, but there is a substantial overlap. It's not like they are perfectly separated. We can now fit a regression line to this, like I'm suggesting up here. Perhaps it would look something like this. I don't know. I haven't really fitted it, but this was just a guess from my straight regression line. And of course, we can see immediately that this actually is a very bad model for this data. It doesn't. This data doesn't sort of lie along a straight line like this, right? Because first of all, there's nothing in between here, and all of them are out here, and they are really not on a straight line at all. They are on two straight lines, you could say, but they are on different levels. But at least this is possible, and now when you do the classification or prediction, you will see that, okay, everything below here will now be classified as belonging to class 1, which is female, right? So if you come in with a new lizard that weighs like 7 grams, or I guess it's grams, then you will go up to the red line here and you say, okay, there is classified the Y dummy hat is like 0.8. So this is closer to 1 than to 0, right? So everything to the left of this green here will be classified as female, and everything to the right as male. Now this idea is kind of stupid, but it works to some degree, and this is now sort of the entrance point, you can say, to our topic today, logistic regression, because we use the regression here, but the problem with this approach is the straight line. We can see that the data doesn't follow this straight line. Could we replace this with something better? That sort of is more following the trend of the data. And that's exactly what we are going to do now. First of all, let me recall from basic statistics the binomial variable. What is this? Coin flipping. This you surely has heard of. Imagine you have a sort of a data generating machinery where you have two possible outcomes, and coin flipping is such a case, heads or tails, right? You flip a coin, it ends up with either heads or tail. The probability P of heads or 1 minus P for tails, it doesn't matter which one of these two you focus on, it's the same each time, right? So each time you flip the coin, it's the same probability of ending with a head or with a tail. And I mean, if it's a fair coin, the probability is 1/2 for each, but it doesn't have to be 1/2. It could just be 0.1, 0.9, right? It could be very skewed towards one of the outcomes. It's still binomial, as long as this probability stays the same. And then you have independent coin flips, so that the outcome of the next is not depending on the previous one. Then you have a binomial situation if you now count the number of heads or tails. I mean, this is always symmetrical, right? So when I say you count the number of heads, you could just as well turn it around and say you count the number of tails. It's just that you have to sort of select one of them as your sort of target class. So the binomial variable is simply the number of heads based from n such coin flips. And then we say that y, if that's the variable, is binomial with n and p as parameters. N is the number of coin flips, it's an integer. P is the probability of head each time. Now the lizard data, this resembles this in some sense, doesn't it? Because this sex, that the classification variable, has two outcomes, male or female. We observe n independent lizards, so that's like the coin flips, right? And the probability of female and male, of course, is the same each time. So this resembles a coin flip situation. So the number of females that we observe is sort of a binomial variable. But wait a minute, is this last one here really true? Well, the probability of female depends on the mass, doesn't it? That's what we saw in the previous slide when we plotted the data. We saw that if the mass is very small, we are to the left, then the probability of female is pretty big, because almost all the females are smaller than the males, right? So do you have a small mass, the probability of female is rather big. On the other hand, if mass is very big, it's a large mass to the right of the x-axis, then this probability is not that big anymore. So it's not really, the last one here is not really true to make this completely into a binomial situation. However, let's see how we can approach this anyway. Consider now local regions of mass. So instead of consider the whole x-axis, we split it into intervals. And for each local interval, we count the number of females. And what is the probability, or actually proportion, of females in that interval, right? So here we have the data again. Instead of considering all the data simultaneously at once, let's just split it into regions. So here we have the first region. And inside here we make sort of one coin flip, and the probability of female is 1, because 1 out of 1 ends up as a female, right? In the second region we make 2 coin flips, and again we have 2 out of 2 are female, so the probability or the proportion of female is still 1. In the third region here we see something starts to happening. Here we make quite many coin flips, and now we see that there are not only females or males, now there is a sort of a mix of them. So here the proportion of female will now be like, I don't know, 60% or something like that, down here somewhere, right? And then you move to the next region and next region, and when you come over here, you can see that here we are down to the probability of 0 for a female. In this region there are no females, and here and here. So we have sort of moved from a very high probability of female down towards a very low probability of female. But in each region we can sort of argue that the probability is constant within each region. So inside each of these thin intervals, this is binomial. So by making the region slimmer, the P is constant, more or less, and becomes more and more constant the slimmer these regions are made. But it may vary between the regions, of course, as we saw. And then the N also varies between the regions. So that's but inside each region it's binomial, but with different p and different n. What if we now make the region so slim that each single data case is its own region? And that's exactly the reasoning here now. Make it binomial with n equals 1. So make the regions more and more of them, thinner and thinner, until they are sort of infinitely thin. And a binomial variable with n equal to 1 is called a Bernoulli variable. It's just a different name for the same thing. And a Bernoulli can only take two values, either 0 or 1. Right? Either you have 0 female on this, it's like you do a single coin flip, right? You have 0 heads or you have 1 heads. There is nothing in between, right? So notice how this is now our dummy variable again, 0 or 1. But now it means counts, right? It's a count of females in this case then. And then we assume that P changes gradually now along the x-axis here, right? So actually what we have achieved by this reasoning here is that instead of modeling the sort of the categorical variable as a function of this predictor, we model the probability, the binomial probability or Bernoulli probability as a function of this mass or any other predictor we may have, x, right? So our model now describes how this probability changes by x. That's what we are going to do now. And that leads us to the generalized linear model. So here are the data again. And now we introduce what is called a link function. We could try to do it like this, and that's the dummy regression that I introduced, right? Where you say that, okay, you try to, or yeah, you say that the probability is sort of a straight line, right? This describes a straight line in x, right? X is now the mass, right? And with some error term. But this is not how the probability. It's not following a straight line, right? So instead, we make a generalization of the linear model. And we keep the right-hand side as before, but we say that, okay, whatever we observe here, or it's not directly influenced by this linear combination, but it's a function, a link function we call it, of this observation that is affected by the linear relation here. So g of p is now a function of p. We haven't said which one yet, but you can easily see that this makes it more flexible now, because it doesn't have to be relating to the response directly, but to some function of the response. And in the case of logistic regression, this link function of g of p is exactly this one. Exactly this one. It's a log of p divided by 1 minus p. And notice that this is now the probability of female in our example, and this is the probability of male. So you have the probabilities of the two classes actually, one divided by the other, and the logarithm of that. That's the link function we will use here now, and this is called the logit link function. And that's commonly used when you have data of this kind, where you have where you count the number of occurrences to be either 0 or 1. Bernoulli data. So this here is now what we call a generalized linear model, and with the logit link function. You will see next week that we can replace this logit function with some other function here and get another generalized linear model. And actually, if you say that the G of P is equal to P itself, then you're back to the ordinary linear model. You see that? If this doesn't transform P at all, then you're back to the ordinary linear. Yeah. Note here that the probability P is the probability of what I would call the target class. The one up here, right? The class that you sort of count heads, right? In your coin flipping. And this is sort of important when you do this in R, because you have this response with which is a factor with 2 levels, right? We have a response now, factor with 2 levels, and the level number 1 in this factor is what we call the reference class, and level number 2 is the target class. And the probability we talk about is the probability of the target class, right? The probability in the numerator here is always the probability of the target class, while this one is the probability of the reference, which is always one minus the other, right? Since there are only two outcomes here, right? So please remember, because this has to do with how you interpret this value, of course, right? You get the probability of 0.6, but is it the probability of male or female? You have to keep that straight, right? So in this case, it's female, because I chose female as the target class. And there's no reason you can't flip it around, of course. Let's go into R and have a look at exactly that. So let's have a look at this lizard data here. And let me just copy this code so we can have it in R and have a look at it. So I made myself a new script here. So save and run. And the data set is called lizard with a capital L. And let's have a look at it. You can see here is the response, sex, right? F and M for female and male. So there are lizards of both sexes here. And then we have some measurements. And let's focus only on this mass variable now. We have 2 others. We can see, look more at those later, but let's focus on only the X, this as the only X now, to make things simple. So the first thing we can do, and we should do, is of course plotting. And here is how I would plot this data with as points, and you saw that actually in the lecture slides, right? A similar plot. So let me just make that plot here. And notice this is not exactly what you saw in the lecture slide, because notice now I used on the y-axis the categorical variable directly, right? This is not a dummy variable 0 and 1. It's male or female. And it's possible to plot like this in ggplot, and that's nice, right? Because here there is absolutely no confusion which class is which, because here the class labels are displayed, right? F and M, male and female. And then you have the X variables over here. So that's nice. You should always make a plot like that. However, let me copy this code. In order to make a plot like I did in the lecture slides, we should add a column now to our data table. So if we inspect the data table here, we can see that here is the categorical response now, and here is the X. So what I do here now is I add another column called female, and then I use this construction here, if else. You may have seen this before. So it says if the content of the sex column is F for female, then this variable here will have the value 1, otherwise 0. So this is counting, right? This is counting. And now think in terms of the lecture where we split the x-axis into super thin regions, right? So for each new observation, for each new data case, I now consider that as one single coin flip. And then I count the number of females for that coin flip, you could say, for that lizard. It's either 1 or 0. Either it's female or it's not. So this, by running this code here, we can inspect here and see we have now got a new column here where it's 1 each time it's a female and 0 each time it's a male. So this is basically the same information, right? But it's coded numerically instead of as a categorical variable. It's now numbers, right? Because it's counts. And then we can plot with this variable on the y-axis instead, of course. And the plot looks more or less the same, but notice the y-axis is no longer categorical. It's now numerical from 0 to 1. And it also marks the values in between, but there are no observations between, right? Because on each data case, you can have either 1 female or you can have 0 females. You can't have a half a female on the lizard. So, making that extra variable here is not strictly necessary, but it's nice to have it for plotting. We will see later. So it's not something you have to do. It's not something you have to do, this step here. Not required, but it's nice to have for the plotting. We will see. Let's now fit the generalized linear model to this data. And here is how we do that. Fit GLM to data. So that's the important thing here. And notice we use a function in R called GLM, generalized linear model. And notice we specify the model in the same way we have seen before with response. And notice now is the categorical variable here. We don't use that new dummy variable. You don't really need that, as I said, other than for plotting. We use the categorical variable as response, and then whatever you want here, and this time I just want mass. We need to say where the data are, and this is important because the GLM function can fit many different generalized linear models. And when it comes to logistic regression, we always use the binomial family. And that specifies the link function. This specifies the link function, the logit link function. So please remember that to always add this family equals binomial. I think that if you don't say anything here, the family you get is the Gaussian, meaning that it's the identity. So you get a linear model instead of a generalized linear model. The same as if you use just LM directly without GLM. And that will fit this data really poorly, right? Then we are back to that dummy regression. But this is now logistic regression with the family equals binomial. So please remember that. We can do that, fit, and it takes almost no time. And we can inspect this object here if we like. We can have a look at it, and it contains a lot. Right? So this, we will not dig into everything here by far, but we can recognize something here. For instance, the fitted values, coefficients, residuals, right? This is something we recognize from LM objects as well. So it's not super different. It is sort of the same. So the fitted values, that's something we can add now to our object in order to make some plotting, because we want to see how did this fitted value sort of fit the data. We always do that when we do regression as well, right? We sort of plot the regression line together with the data, because that's nice. It gives us sort of a, how does the regression line fit the data, right? That's a good visual sort of impression of the model. And that's what I do here. I take now again the lizard data table, and I mutate in again another variable that I call female probabilities, and that is exactly the fitted values from that GLM object. So I put them into a separate column, and then I plot again, and notice now I plot in the same way as I did up here, with X equal mass and Y equals female. So I will get this plot we see here. But then I also add another geom here, also with points, with the same X, but now I use this female probabilities as Y instead. And then I color them red. And I make the dots slightly smaller, I can see. I don't know. This is something you can... So let's run this code here. And now you can see how the fitted GLM model sort of indicates the probabilities of female. So here we have a probability of female very close to 1 for the small mass, and then we can see as we move to bigger and bigger mass, the probability of female is now dropping, and then it goes towards 0. So out here we have close to 0. And notice the shape of this sort of curve here. You can see that there's sort of a curve, right? We could have plotted it as a curve as well instead of points. It's this sigmoid shape, this S-like shape, except that it's reversed. It's upside down, you could say, S. But that's the point, that logistic regression fitted models will always give you a shape like this S-like. So it's not a straight line anymore, and it levels out here, so it never goes below 0 and it never goes above 1. Stays in between 0 and 1, which it should for probabilities, right? And that's the reason for that logit link function. It's trapped inside this interval 0 and 1. Okay. The importance of factor level, yeah, because factor level 1 is a reference and factor level 2 is the target level. And if we actually if we inspect our data, right? If we plot it like this, then we see the levels listed, and we can see male is level 1 and female is level 2, because they are always listed in their ordering here. So M is now the reference and F is the target. Of course we can flip this around, and that is exactly what we do here in this code. We just flip it around, and let me show you that this produces exactly the same result, but it's only sort of mirrored. So now I make the lizard2 table, which is the copy of the lizard, except that I just swap the levels, right? So now I set female to level 1 and male. So female is the reference and male is the target. And then I also make a new male column as this Bernoulli counts, right? So if I do it like this, the lizard2 dataset will look very similar to the lizard dataset. So you can't really see a difference here, but now if we lizard2, now you can see that they have been reversed, these factor levels. And if we now fit a GLM model to this data and then do the plotting, you will see everything has been reversed. So now 1 is the number of males, right? Not the number of females. And the GLM model describes now the transition this way instead of the previous one. It's simply a mirroring. So the outcome is exactly the same, but you have to keep straight in your head when you talk about the probabilities here. Is it the probability of female or male? Which class is the target? Right? Which class is the target class? That's factor level 2, right? So that's important. Some GLM technicalities. I mentioned that the GLM link functions, there are several of them. And actually, the ones we will see are these. The identity function, well, that's the one we have used all the way up to now, because it assumes normal distributed response. So it's actually the same as using the LM function. So I mean, if you have data where you need the identity link function, you don't use GLM at all, you use LM, right? And then it's not this is the special case, right, of a linear model, not the generalized linear model. But it's formally among the link functions, right? This one changes nothing, you could say, to the response. Then we have the logit that we saw now, and then this assumes the responses is classes, right? So it's a categorical response with two classes then, with this logit function. Two class classification. We will see in a minute that we have we can extend it to multiple classes, and then we use the logit, but we use it several times in a sense. And then next week we will see the log link function, and that's what you do for count data, where the count is no longer Bernoulli 0 or 1, but some bigger numbers, right? 2, 3, 4. Yeah. I just mentioned it. So I should also mention that instead of the Bernoulli data that we focused on now, so making each data case a separate sort of Bernoulli variable, you can actually turn it into proportion data. Imagine that even if you make if you split this x-axis into thinner and thinner regions, you can still end up having this several data cases having exactly the same x value, right? Especially if you have categorical x's, that will happen straight away. Then you can, instead of splitting it in each data case into a separate Bernoulli variable, you can split each unique x value and into a different case, right? And then you count the number of both outcomes in for that x value, right? So it's no longer n equals 1 for each data case, but n can be bigger than 1. Let's say you have, for the same mass, there are 3 lizards, right? Weighing exactly the same thing. Then you have 3 count, right? So it could be 1 female, 2 males, for instance, or 3 females, 0 males. It means you have to count both the outcomes. And the response to the GLM function can actually be a matrix with these 2 columns, heads or tails then, males or females, right? So instead of having a single column as a response, you can have this 2-column response where you have counted both the outcomes. And if you want to read more about this, you can see it in chapter 16 of the R book. But we will not pursue this here. And I have to say, the results you get, whether you do it the way we do it here now, or if you do this proportion, the results you get are exactly the same in terms of fitted values, regression coefficients, p-values, etc., etc. So it doesn't really make any difference whether you do it one way or the other, but it has this flexibility, I would say. It could be that this proportion counting is sensible in some settings. I don't know. This is not something I do frequently, so I can't really be a judge of that. But no, just be aware that this is a possibility. We will not talk more about it. When we fitted the GLM model, we got again a maximum likelihood fit to the data. And this is very nice. And the reason we can get a maximum likelihood is because we have an assumption about the distribution of the data. So the data is assumed to be Bernoulli or binomial if you do this thing. And once you have an assumption of a distribution, you can in principle get a maximum likelihood fit. And why is this so nice? It means we can compute this Akaike's information criterion, AIC, that we have seen before, for each fitted model. And we will see that shortly. So a nice sort of byproduct of maximum likelihood fitting is that we always get these AIC values, meaningful AIC values. I should also mention the deviance, because this is something that pops up in the output of when you do the summary of this GLM fitted models. You will see deviance listed. We will not dig into it, but it's a measure of lack of fit to the data. So you remember from straightforward regression, we compute this R square, right? And if you go back to our previous weeks, you will see how we defined it. It's the residual sum of squares divided by the sort of the total sum of squares. And 1 minus that. Think of deviance as this residual sum of square. So a smaller deviance means a closer fit to the data. The smaller, the closer fit you have to the data. So it's sort of, what should I say, the GLM variant of R square. Except that an R square, the bigger the better, here the smaller the better, right? Smaller the better. And it's always listed together with the degrees of freedom. And as a rule of thumb, you can say that the deviance should not be much bigger than the degrees of freedom for a model that fits the data well. If the deviance is much bigger than the degrees of freedom, it means a poor fit. If it's super small compared to the degrees of freedom, it could be an indication of overfitting. Yeah, we can perhaps come back to that. Let's turn to this concept here, odds ratio, because this is important. In a linear model, when we fitted a model, we were always interested in the slopes, right? And for a single x variable, it's beta 1. But if you have many x variables, there are many corresponding betas, right? So we are interested in the slopes. How much does the line or the plane, I mean, if you are in higher dimensions, how much does it sort of tilt in that direction? That indicates the effect, right? The effect of the predictor variable on the response. So a slope. And a slope means when you increase the corresponding x value with 1 unit, right? How much do you rise or fall in response? That's what the slope tells you. So what is the meaning of this one now? When we have this logit GLM, there is no slopes anymore, because we saw that the fitted line is no longer a straight line, so the slope changes all the time, right? It's meaningless to talk about a slope now. So what is this beta 1? Let's have a look at it. Here is the sort of the model that we start out with, right? The response is this logit of p, which is then a linear function here. And here we have beta 1. If we now make yeah, we can just take the exponential on both sides, so we get rid of this log here. Then you can see that this fraction here is now the exponential of this linear relation here. And again, if you solve for p now, you get this expression here. So this is actually how p is modeled as a function of x, right? Quite sort of complicated in a sense. This here is something we call an odds. And that's something you may recognize if you have been betting. If you do some betting, you may be familiar with the concept of odds. So what is an odds? Notice here we have the probability. We have sort of two outcomes, right? This is the probability of the target class. This is the probability of the reference class. So if you have two outcomes, the odds of the target is this one. The probability of the target outcome divided by the probability of the other outcome. That's what we call an odds. And we can see that this in this concept here, it's just, if we call the odds just d of x as a function of x, this is the function, right? This is the odds as a function of x. So this changes by x. The odds ratio, that is now exactly this one here. If you increase x by a unit 1 and look at the ratio between the odds when this one was increased by 1 compared to the original odds, then you get this expression, right? And then you can see that you can now we can now cancel some terms here, so we end up with this simple. And here you can see beta 1 is now found. So actually this is called the odds ratio, and it's the ratio between two odds. And that is what this beta 1 describes, and it's e to the power of beta 1 actually. So it says the odds in favor of the target class increases by a factor e to the power of beta 1. So beta 1 is no longer a slope, but it's sort of similar because it tells us how this odds ratio changes. Let's look at a couple of examples. So let's say we estimate beta 1 to 1. It means that the odds ratio is then e to the power of 1, which is around 2.71. That means that if you move to the right on the x-axis, the odds for the target class increases by a factor 2.71. So it grows, right? It grows. The odds for the target class grows, meaning that the probability also grows. Remember the odds, right? It's the probability of the target divided by the probability of the other class. So when the odds grow, the probability grows. On the other hand, if we estimate beta 1 to some negative value, for instance minus 1/2, then you can see that the odds ratio becomes smaller than 1. So now the odds shrinks, right? It's a factor 0.6. So it goes down. And that means the probability is dropping for the target class when you move to the right on the x-axis. Notice that the odds ratio never becomes negative. If beta 1 is negative, it only becomes less than 1. So the odds ratio cannot be negative, but the beta 1 can be. And notice it's exactly the same. If beta 1 is positive, the target probability grows. So it's sort of an increasing function. If the beta 1 is negative, the target probability drops. It's a decreasing function. So the sign of the beta 1 is the same as when it was a slope, but it's not really a slope anymore, but it's an odds ratio. And also, of course, if this beta 1 is 0, it means that the odds ratio becomes 1 and the probability doesn't change. Right? If you move along the x-axis, the probability of the target class doesn't change. That's what an odds ratio of 0 or of 1 says, a beta 1 of 0. And notice that this is exactly the sort of situation that says there is no effect of the x variable on the response. So it means that no change in odds means no effect of the probability of the target class. So again, we can make the null hypothesis saying beta 1 equals 0. exactly the same as we did for regression when beta 1 was a slope. A slope of 0 means no effect. And in the GLM, again, a beta 1 of 0 means an odds ratio of 1 and no effect. So this is again a meaningful null hypothesis versus there is some effect, right? Positive or negative. Instead of making a t-test, then we now get what is called a z-test. And that is because the test observer is no longer t-distributed. The nice theory we have for linear models doesn't hold anymore for these generalized linear models. But an approximation is to do it like this. Say that, okay, it's not t-distributed, but it's probably not very far from a normal distributed, this test observer. And actually you can think of a t-distribution as a normal distribution, as a t-distribution with infinite degrees of freedom. But this is sort of an approximation. And remember this, that the GLM p-values are not exact anymore, like they are for the linear model. So I would, for practical purposes, I would say, okay, I would require p-value. I would be slightly stricter here. P-value should be really small now before we reject the null hypothesis. Okay, let's go back to R and see how we can compute some odds ratios. So, odds ratio and significance. We have fitted the GLM model. And we actually did it twice, but let's forget about this last case here where we just reversed everything. Let's go back to the original one up here, right? We can make a summary of a GLM object just as we are used to with the LM objects. So what happens if we do? Let me show you here. So now we have, let me just take out this. We have a summary output that is somehow similar to what we have seen before. We have again the coefficients here, right? And the intercept with an estimate, and this is sort of the beta 0 estimate, and this is the beta 1 estimate, right? Coefficient for the mass. And this is, as you remember, this is no longer a slope, right? But e to the power of this is an odds ratio. And the standard error, and here we have a z value instead of a t value, and we have a p value. So here we can see that based on this one, we would say on a 5% level, we would say this is probably significant. We have a effect of mass on this classification, right? On the probability of female. That was the case here. We can also see that the residual deviance is output here is 21.8 on 23 degrees of freedom. And I mentioned this deviance should be not much bigger than the degrees of freedom, and it isn't here. This looks fine. And here you can see we have also an AIC value output. And this means really nothing as a value, but it's for comparing against alternative models. We will see later. But let's focus on this one here, the estimate beta 1. So what about this odds ratio? So we have estimated it to some value, and then we can compute the odds ratio, and that is simple enough like this, right? So this is the odds ratio then, 0.41. And this tells us now that if you increase mass by 1 unit, the probability of female drops because this is smaller than 1. And the odds will drop to 40%, right, or what it used to be. And that also, I mean, if I go back here and plot this plot again, this odds ratio being smaller than 1 is of course the same as this red curve dropping when you go from left to right here, right? It's dropping, it's not increasing, it's going down. So that's what this odds ratio tells us. And since we have now a significant effect, right, it means that this is the mass variable is a sort of carries substantial information about classification between the sexes here. And it's going down. The probability of female is going down with this much, or not. This is not the probability, this is the odds, right? The probability, the change in probability is depending on where you are on the mass axis. It's the steepest here, of course. But this is not depending on that. This is the odds ratio is the same throughout. Okay. So what do we do if we have more than two classes? So everything we have seen up to now is sort of a machinery that works for two classes. Well, the idea of a binomial with two outcomes may easily be extended to a multinomial with many outcomes. So we can actually take the same idea and expand it. And again, we choose one factor level as a reference, and then all the other levels are targets that are sort of compared to this reference class. So we always sort of compare the other classes to the reference, and this is different from LDA, for instance, where we could have multiple classes and all are sort of compared against each other. All pairwise comparisons, you could say. This is not the case here now. So level 2 is compared against level 1, level 3 against level 1, and so on. So that's the difference. So you can say that instead of having one binomial, we now have several binomials in a sense. And we estimate probabilities for target class K versus the reference. Yeah, that's always sort of, the reference is always fixed in a sense here. So you can actually write it like this, where you have now K target classes, right? Or K indicates which target class. So you have the same logit function, but notice now instead of P and 1 minus P, this is now the probability or the reference each time. While this one changes now depending on which target class you are focusing on. But it's this linear combination, but notice that beta 0 and beta 1 are different from each target class. So you estimate new beta 0 and beta 1 for each target class. And this P1 is then simply just 1 minus all the other target probabilities, right? So that's sort of the same denominator here. But it's the same logit function, right? But it's only one for each target class, you could say. The classification. Once you have fitted the objects, we get estimated this posterior probability. So this is what we get directly now, sort of, from this logistic regression type of fitted models. We saw that we get the probabilities, right? The fitted values are exactly these posterior probabilities. So wherever you are along the x-axis, you get a probability for the target class. And then you have for the reference, right, as the alternative. And Bayes' rule says, again, assign to the class with the largest probability. So the classification step here is not really anything at all, right? Once you have these probabilities, it's obvious where you classify it. If you now have a new test set of data, then you can use the predict function to do this classification. And you should notice, and we will see that in our session, that this predict function behaves different from whether you have fitted a GLM function for the ordinary logistic, or we have an alternative function called multinom when we have multiclass. So we will see that this predict function behaves slightly different whether you input this type of objects or this type of it. I don't know why. This is a little bit unfortunate that it's difference here, but that's how it is. Once we have a classifications, we may of course compute this confusion matrix and accuracy, and as we did last week, I will not sort of repeat that because that's pretty obvious, right? Once you have classifications, you can do exactly as we did after LDA or QDA. It's only the way you compute this one and that separates actually LDA from this logistic regression. So let's go into R and have a look at how we fit a multinomial model and do some classification. So let's have a look at how we can do logistic regression with several classes. And we will use this poems data again that we used last week because this data set is familiar. So let's copy some code here. And let me make some multinomial regression, we could call it. So notice I need to use a function from another R package called nnet. This is the GLM function will not take multiple classes. It will only take the 2-class problem. So in order to extend it to this multi-class, we need this nnet package. So you need to install that and load it. And then I load the poems data. And here is how we fit that now. And notice now we use multinom instead of GLM. We use a formula as before. You don't need to specify a family because it's obvious from this that this is a binomial family. Notice now in that data set we should actually have a small look at this poems data set just to remind ourselves what is this? What is this poems data set? Well, we have the classes are the authors of some poems, right? There are 3 authors, Shakespeare, Blake, and Eliot. And for each poem, we have counted the frequencies, the relative frequencies of the letters that the authors used, right? So this is the fraction of A's that Shakespeare uses, right? In the poems, right? In the various poems. So there's a new Shakespeare poem, and this goes on for the Blake and Eliot poems as well. And then we see the fraction of B's, the fraction of the letters, right? So this is, and so on for all the letters, and also for some comma and semicolon and spaces and so on. Yeah. So it's actually just counting the number of symbols that you find in the text of each poem. To make this easy now, we only use this column as a predictor, A, right? Only one column as an X variable. And I could have chosen any one of them, but I chose the first one randomly, you could say. So we fit a multinomial model with author as the response, the classes, and only one predictor called A, because that's the name of that column, right? But you can choose any other if you like, just to see how it will, of course, result in a slightly different result, but it will result in something. And notice here that this reports now some iterations during its fit to the data. So you can see how it starts out fitting the data and ends up here. It's not important. Topped off 100 iterations, okay? Let's look at the summary output. And the summary is really short, but we can see that we got some coefficients estimated here now. And notice, yeah, that we should probably have. We should have poems author. We should have inspected this, seeing that Blake is now the reference. level, right? The reference class. And Elliot and Shakespeare are the two target classes. So here we now get estimates for the two target classes. So for Elliot, we have an intercept. So this is beta 0 Elliot, you could say. And this is beta 1 Elliot, 57, right? For A. And here we have now similar for Shakespeare, a beta 0 and a beta 1. And notice again we have an AIC value output here. This is nice. Maximum likelihood. Okay, so we have some, but there are no p-values here. There are no p-values on these estimates here. But we have, here, these were the standard, oops, these are the estimates, whoops. These are standard errors, right? Yeah. These are the coefficients up here. I looked at the standard errors. These are the coefficients. So we can see that, okay, there is a negative on A here and a very negative on A here. But we have some standard errors for the estimates as well. And actually, I can, we will see how we make use of those standard errors. Let's try to make a plot of the fitted values here and the outcome and how it looks like. And this is not so straightforward anymore now, because how on earth do we actually plot three classes along the A-axis here? So first of all, I want to have the fitted values, of course, and we should actually have a look at that multi-object has a fitted values somewhere. There it is. And notice this is now a matrix, sort of a table, right? Because now you don't have probability of a target class, because you have two target classes, right? So now we list the probability of all three classes, actually, the posterior probabilities, right? And this is very similar to what we saw for LDA. So this for the first observation, this is the probability of this being a Blake poem. This is the probability of being an Eliot poem, and this is the probability of being a Shakespeare poem. And this is by far the biggest one. It's 87, 0.87, right? 0.88. While these two are pretty small. So all the values in a row here now sum to 1, because it must be one of the three, right? Each poem. So now you get the posterior probability for each poem here listed. Okay. And this is what I wanted to plot now. So I add this to the data table, and then I select only the author, the X variable A, and these three, because notice they have the names of the, I know that they have these names, Blake, Eliot, Shakespeare, that's the factor levels, right? So I can select these variables. And then I put the columns under each other, these three columns here. So I turn it into a sort of a long table. I can actually do this step by step a little bit, so that we can, if I stop after here and run this part and look at this TBB table, this is how it looks like, right? The author, the original sort of class variable, the X variable, and here are the three posterior probability columns, yeah? And then we extend it a little bit to here to make this, use this pivot longer function to stack these, we select everything except column 1 and 2, and then we stack them. So if I run this one now and again inspect, so now you can see these probabilities, the posterior probabilities have been stacked under each other. So here we now have for the first poem, The first 3 rows is for the first poem. And this one indicates now which author it's the probability of. And this is the reason I do it like this is for the plotting that comes now here. So now we plot this, and then I put a line with x equals a, of course, which is the x-axis, and y is this probability. And I color it by class. So I have this fitted curve sort of for each author. And then in addition, how do I sort of plot the data now? because it's sort of tricky, but I decided to do it like this. I put now a bar on each x value with a different color depending on the author. So we can see that the bars changes color as we move along the a-axis. So let's make the plot, and you can of course inspect this code in peace and quiet. So here we see the x-axis, the a fraction, right? And we can see that when this fraction of a's is low, we have all the Shakespeare poems, the blue bars here. They are with fairly low values for a, while over here we have the red and green bars indicate the Blake and Eliot poems, right? They have more a's in them. And even one out here, right, which is a Blake poem with lots of a's. So that's a special one. And now you can see the fitted curves here, indicating that as long as we have very few a's, the probability of Shakespeare is really high. But then it starts dropping, and at the same time the probability of Blake and Eliot, but they are almost the same. Can you see that? Blake and Eliot is almost the same. So actually it turns out that Blake is never the winner here if you, in terms of the posterior probability. So imagine you have a new poem now, and you have count the fraction of a's in it, and it's here. How do you classify it? Okay, this is the probability of Blake, the red one. This is the probability of Eliot, the green one, and this is the one of Shakespeare, blue. So this will be classified as Shakespeare, right? But if you are over here somewhere, you will always, the green one is the winner. And notice the red one is never the winner here. So, and this can easily happen, of course, right? As long as we have only one x variable. It could be that one of the classes is never sort of characteristic of this x variable here at all. Okay, so that's an attempt to plot it. I mean, there are many ways you can plot this data. Let's see how we can compute some p-values, because there was no p-values in the summary output. So let's have a look at the code here of how we can do this sort of ourselves. Computing p-values. I'm not sure why this is not done by that function, because it should be sort of straightforward. So the summary that we are used to just outputting to the screen, in the console screen here, we can just store it as a list. So let me do that. If I, instead of having it output to the screen here, I store it as a list here, summary. So here we will have some quantities that we can extract now from this list, right? Instead of having them output on the screen. And then I make a table here where I use the coefficients from that summary and divide by the standard errors from that summary. That's we saw it earlier where I confused them. We get coefficients, and we also get standard errors for the same coefficients. So that's what I do here now. I compute that for each of the coefficients, and then we can take that table and mutate in a new class variable, which is actually just the row names. And then we do this pivot longer again to put things under each other and so on. Let's run this code to actually see what happened. sum list Z table. And now I want to look at this Z table here. Yeah. So now I have for each class, target class, the intercept coefficients, its set value and p-value. So here you can see that for Elliot, the p-values are really high, right? There is no information in A using the A variable as X variable. There is no information in it that separates Elliot from Blake, because that's what it means, right? We always compare the target class to the reference, and that we can obviously see here, right? There is no information using only this X variable here that helps us separate Blake from Elliot, because they are very similar in terms of how they use the letter A. So the p-values are super big. But for Shakespeare, it's different. Shakespeare really separates from Blake then here. And that we can of course see by the plot itself. All the Shakespeare poems are down here. All the Blake poems are up here. So this is a very good, there's significant effect of Shakespeare, significant effect of A when it comes to classifying Shakespeare from Blake. Let's have a look at classification then for two or more classes. So let's go back to this two-class problem again of the lizards. And we have fitted this GLM object. So this is how you actually do the classification now, I would say. We predict the probabilities actually. So we used now the GLM object that we fitted earlier, and the new data, we don't really have new data, so we used old data again as new data. Well, that's a sort of cheating, but it's legal, right? So it's not really a test of how well we fit, how well the model fits this this data, because we use the training data for test here now, but we can at least do this to see how well it separates within the training data. And notice type equals response. This is to get the probabilities as output. If you don't specify this, you get some odds output. And that's difficult to interpret. So we typically want the response type of output, so we get probability. Let's see what happens if we run this one. So what is this? Female prob now. It's now a vector where we have now for each of the lizards in the same order as they appear in the dataset, the posterior probability, right, for female. So now you have to remember what is the target class here. So these are the probabilities of female. And of course, once you have this, you can now do the classification by just assigning to the class with the largest probability, right? So I make myself a new table where I just put female probability as one column, male probability is then just 1 minus the female probability, and then the classification, I use this if-else construction again. If female probability is larger than half, then it's female, otherwise it's male. And then I just simply mutate this into a factor again as it was before. So once I have this lizard prediction table here now, where is it? There. There, I can open it. Then you have the posterior probabilities for the two outcomes, right? Even if the predict only gave us the first one, we can of course compute the second one because it's always 1 minus the first. And then the predicted classification. So this is not necessarily correct. This is the predicted classification. And if you want to do some confusion matrix and so on, you can now compare to that, to the true classification. Let's instead see how we do the prediction for the multinome model. Classification with multi-class, right? Object. And we use the same predict function, and now we input this multi-object, and we don't have to specify any type, because this will directly give us the classification. Oops. Directly, without, it doesn't give us the probabilities, right? It gives us the classification directly. So here we can now see all the first poems are classified as Shakespeare, all the other ones as Eliot, none of them as Blake. And that follows from the figure here, right? So we can actually make prediction of probabilities as well here, but then you have to specify that you want type equals prob, right? So if I just copy this one, author prob, should I call it, like this, and look at it here, then you have the probabilities for each author here now. So if you want to have an output exactly the same as we did for the lizard data here with 2 classes, you can do it like this. But if you want to have the classifications in the end, you can get it directly here. You can't do that up here. You have to first compute the probabilities and then do the classification. Yeah. Posterior probability. Again, everything sums to 1. So you can see that the winner is either Eliot or, even if it's sort of close, right? For instance here, 51% Eliot, 48% Blake. So it's a rather uncertain classification of Eliot. So that's something, the posterior probabilities are valuable, I would say. Variable selection. Yeah, this is a topic we have seen before. With binomial or multinomial logistic regression, we may of course also have several predictive variables, and typically numerical, but may also contain some categorical variables, but typically numerical. But we can have many of them, and that we have seen before. Which predictive variables carry information about classes? This is typically a question, I would say, that we dwell upon here in STAT340, because we are not that concerned about how correct we classify, but we want to understand which of these predictors are the important ones for doing this classification. Where is the link, you could say, between the X's and the response, the classes? So both GLM and multinom give us these AIC values that we saw briefly, and that gives us an opportunity for starting to make variable selection, because what we can do, at least in principle, we can fit different models using different combinations of predictors and then rank them by this AIC, and the smallest first, of course, because we know that the smaller the AIC, the better the model. Sort of, it's we have talked about the AIC criterion before, and it should be as small as possible in a sense. It balances the underfitting versus the overfitting, right? And we can easily have overfitting with classification data as well, and on underfitting, of course. So this is at least one way of approaching the variable selection, using AIC and then try out all kinds of combinations of the predictor. And this is doable for a smallish number of predictors, but if you have really many predictors, this is hardly doable. And remember that if you have p larger than n, you have this collinearity problem as well, so it may not be even possible to fit all different combinations, right? But this works for in many cases, you could say, but not all. What do we do in those cases where we have super many predictors, or we can actually use it all the time, but especially in those cases? Well, we can use the lasso again, and that we saw earlier, the lasso method. If we have p larger than n variable, especially then, this is really convenient. And actually, we may use exactly the same procedure with the logistic regression, because the function in R that we used for running lasso, it was from a R package called glmnet, if you remember. And it lies in the name of it, glmnet, that this can handle also GLMs, generalized linear models. So you actually just specify the family binomial or multinomial in the same function that we used for regression, where we didn't specify anything, because then you get the default, which is Gaussian, the identity, right? Link function. But by specifying either binomial if you have two classes or multinomial if you have three or more classes, you get sort of a logistic regression type of model that we have seen now in the glmnet function running this lasso procedure as before. So this is extremely simple in a sense. And we will see how to do this now in a short R or in the last R session. When it comes to variable selection, let's first look at using AIC. And actually, we do this now in a way very similar to what we did last week with LDA. We did some best subset selection with LDA, and that is exactly what we are going to do here now as well. So I copy this code here, is actually the same more or less as we used last week when it comes to the when we did this for LDA. Variable selection with AIC, best subset selection type of idea. So actually I will not go into the details here, but since we now have, okay, that's something I should have specified first. We are now going to use the lizard data again, where we had two classes, but we have three potential predictors. Three potential predictors, right? So if I think I have the lizard data in here, yes. Let's open the data table again. So here we have mass, SVL, and HLS. These are the three possible predictors, right? And then we have the response here, the sex. So since we have three, I have too much open here now. Since I have three predictors, I create this subset table here by using the expand grid 3 times, or on 3 different vectors of true and false. So I get 3 columns, and then I name some, put some name on them, so I have the same column names as in the original data set, and I add a fourth column called AIC, where I put no values, infinite values. And then I take away the last row. Let's run this. This is the same as we did last week. Subsets. It should now have mass, SVL, HLS, and this I will fill in this with sensible values as we go along. But this indicates now how these variables should be combined in each model, right? The first model contains all 3 of them. Then we have the second model lacks the mass, only these 2. The third model uses mass and HLS, but not the second one, and so on. So we have actually all combinations here now by using this expand grid. Okay, Then we do the for loop as we did last week. So we go through each row of this table, fit one model each time, and so I actually make myself a new sort of data table where I select only the columns that are indicated by this row of the subset table, right? And then I fit the GLM with sex as the response and all the variables in that data. I only make sure that I put only the data columns that are part of the subset into there, yeah, and use the binomial. And then I get from this GLM object, we saw it before that these GLM objects contain an AIC value. I have an old one lying here. We can always open it. And if you scroll down somewhere here, no, here it was, there, AIC 25.88. So you will always find an AIC value inside this GLM object. So that's why I copy that into that row number I in that column. So if I run this here now and open the subsets again, now we can see that the AIC values have been filled in. But notice here, what happened out here now? What happened out here? This is something we should be aware of. We got some warning messages here. Yeah, this first one is not important. This is the one important. Algorithm did not converge. Fitted probabilities numerically 0 or 1 occurred. Yeah, that's something that can happen sometimes. And that's an artifact, you could say, of logistic regression. Namely, if you have a variable that really separates the classes well, that becomes a problem for the GLM fitting. And that may sound strange because it should actually be a benefit, right? But if you look into the listed, you can't really see it here, but I think it's this HLS column. I think it's this one that separates the two classes perfectly. And if we go looking into the AIC values, notice where do you have the smallest AIC value? You have it here, right? 4. And that's for this row here where you only include the HLS variable. So this seems like the best model, and actually it is. But notice that the AIC values are actually just integers. It's the likelihood value that is lacking completely from or it's 0 in the fit of these models. That's why they become so strange AIC values compared to the others here. But this is actually, if we now fit a model with only this HLS, what actually happens here? So we can just plot it here first. Let's do that. If I copy this code here and plot it, and notice now I plot with x equals HLS and y equals. So this is a plot similar to what we have seen earlier. Actually, let me take away this plot. But instead of using mass on the x-axis, we now have HLX on the x. And notice here, all the females are up here to the left of this value, and all the males are here to the right of this value. There is a value here along the HLS axis that separates the two classes perfectly. And this actually causes these problems for the fit of the GLM model, because you can imagine this sigmoid shape curve here now becomes infinitely steep here. It's 1, the probability of female is 1, 1, 1, 1, 1, 1 up here, and then it drops infinitely fast and becomes 0 here. That's why you get this 0 and 1 occurred, right? The probabilities. So if we actually fit the model with only this predictor, let me copy this here. Only this predictor, we get this warning, right? This warning. It is only a warning, so the model is actually sort of fitted, but it means that the results you get now are strange, right? Because you have these extreme values. A probability becoming either 0 or 1, that's the bad news, right? And if we plot the fitted data, you see how it looks like. Exactly how I thought. It's 1, 1, 1, 1, 1, and then it drops infinitely fast, and then 0, 0, 0. And this makes it impossible. So actually, how fast should it drop here? There are many choices of parameters here that give exactly the same fit. That's why you get this warning. So it's not numerically stable, as we say. And also, if you do the summary of this model here now, notice the p-values. Isn't this strange, right? Because you can see that the beta 1 is minus 13. It's super negative, right? So you would think that the odds ratio is, the odds ratio is really sort of small here, right? It drops very much when you increase HLS. The probability of female is dropping because of the negative beta 1. But the p-value is not small at all, and that is because look at this standard error. It's super duper big. So, and this has to do with uncertainty in this. The uncertainty becomes very, very large now because of this lack of stability in the fit. So this is sort of an artifact, I would say, of the logistic regression as a method. Because actually, when you think about it, if you're interested in classifying the sexes, the HLS variable should be perfect. I mean, if we had used LDA here now, LDA would be super happy to have a variable like this. But logistic regression is not super happy. It complains that this is sort of too easy. You cannot fit the model to such data because they separate too well. So actually, for logistic regression, there should be some overlap region here to avoid this warning. But you can see you get the result, but you get no p-values then. How about the lasso? How about the lasso? Because this subset selection that we did here is okay when you have like 3 variables or 10, even 10 variables, right? It will be many combinations, but if you have 100 or even 1,000 variables, this is hopeless, right? We cannot look at all combination then. This is hopeless. So this is only something you can do for a smallish number of predictors. Let us instead consider variable selection by the lasso method. And this time let's focus on the poems dataset again, where we have 3 classes. So we use multinomial logistic regression, but there is no reason why we couldn't have done this also for the 2-class situation. It's just an example this. So we will use this cv.glmnet function that we have actually used before. And the only difference to what we did when we used it for regression is that we now specify the multinomial family. Yeah, and it's also a slightly more difference. Let's copy the code here and explain. So let's go back to here. Variable selection with the lasso. So first of all, we need this glmnet package that we have used before, so I'll load that. I set the seeds here just to make this reproducible. If you want to do exactly what I do and get exactly the same result, you also need to set the seed to 1 like I'm doing here. Otherwise, in this cross-validation function, there is an element of randomness, right? So if you don't do that, it will the results will come out slightly different each time. Remember when we used this glmnet function before, we have to input the data slightly different from what we are used to. We cannot use this formula. So we actually have to put the response into one separate vector. I call it y. And the predictors you need to put into a matrix, and I call that capital X here. And then you can see we input them here, X and Y, as 2 separate inputs really. And now we specify family equals multinomial. And this we didn't do before when we used it for regression, because then the default family is Gaussian, which means the identity link function in GLM, which is the same as LM really. So for only ordinary regression you don't specify anything, or you specify Gaussian. But if you have a 3-class dataset that we have here now, the response is a 3-level factor, you use multinomial. If it was a 2-class, like the lizard data, you use binomial. Then I also specify this one here. And what is this? This is not really required, but let me try to explain. When we select the variables now, remember that it's sort of 2 types of problem. No, not 2 types, 2 separate problems. First, we want to separate target class 1 from the reference, and then separate target class 2 from the reference. And it's not necessarily the same variables who are important in the first case that are also important in the second case. However, to make the interpretation and the results easier to grasp here now, if we set this type multi to grouped, we force the glmnet function to select the same variables in both cases, or in all cases then, right? If you have many classes. Yeah. So the default is to not have it grouped like this. And then it means that you will select some variables based on separating one target class and some other variables based on separating some other target class from the reference. And that's okay, but the only difference is that the output and the results are slightly easier to grasp here now. It will not get exactly the same result either, I could say. But it's not a big thing. That's my point. This is not a big thing. You can easily turn it off, but I turn it on now. Grouped or ungrouped is the alternative then. The last one here is the number of test sets when we do the cross-validation, because we now split the data into this number of test sets, right? And since we have rather few data cases here, if we look at this X matrix, it has 22 rows. That's kind of small, right? So we cannot split this into many test sets. That's why I choose 3 here now. 3 is, yeah, then we have 7 and 7 and 8 observations to 22. 7 plus 7 plus 8, that should be 22. Yeah, that's probably what we will see now. So with a bigger data set, I would use a bigger value here. Notice we also have 30 variables now. We use all the variables, right, in this matrix. So this is the frequencies of A, B, C, and so on, all the symbols. So now we want to select which ones of these are important for class separating between the 3 authors, right? Which variables should we focus on? So let's run this code. Set the seed and run the cvit. And now we get some warnings again, but this time it's because we have too few observations really. So we get a warning. It says it's a dangerous ground. Selecting variable based on this few data cases, that's a really dangerous ground. Okay, but we get some results. And then we like to plot. Let me copy this code here. First thing we always do when we have run this GLMNet, the CV GLMNet, is to plot that object. And if you remember from earlier, we got a result something like this, where we have the degree of shrinkage in the lasso method along the x-axis here. We have the error, either as a cross-validated classification error. You can actually have that, but in this case it's multinomial deviance. You can actually change that. That's also an input an argument you can give to this function. How to measure the error, you could say, but I use the default one now. And then up here is the number of variables that are selected. So we can now see that for the minimum error, this shrinkage here gives minimum error. We select 11 variables. And if you go to an even sort of smaller model, where you have error not significantly poorer than the best, you are down to 9 variables, so it doesn't shrink very much, right? So let's look at this one then, the minimum error. And first we need to know which value of lambda produced the smallest one, and that's this one, IDX mean, which it's a lambda value number 87, okay? And then we take out the regression coefficients for exactly that case. So beta mat is now a matrix with one column for each variable, no, so each class, and one row for each variable. And if we put some call names on this beta mat as well before we click it open and look at it, we can now see the variable A has some values here, indicating that this is a selected variable. The variable B is only zeros. This is not selected. So the frequencies of B's is not important for separating between these three orders. Carries little or no information. But C's are important again, right? And we can actually see from the signs here that, okay, A, this really distinguishes Shakespeare's from the other two, right? While C distinguishes Blake from it distinguishes Eliot from the other two, because these two are negative and this is positive. Yeah, and so on, and many zeros down here, and here comes the other one. S is important, T is important, and so on. So these are now the important variables here. And actually the values here I would not really interpret. So what I would do now, I would note which of these variables are selected, and then I would go back here, make a selection from that original data variable here, select select the columns in X that corresponds now to the rows here who has non-zero entries, and then I will go back and fit a model again using only these variables. And then you use this multinom function, for instance, that we used previously, right, on that selected subset of variables. And then you can start interpreting the coefficients and look at p-values and so on.